At 10 centimeters in diameter, over a trillion Planck lengths could fit side by side across the apple. Indeed, it's so large compared to the Planck scale that it might as well live in an entirely different universe. It is so far removed from the chaotic foam of quantum uncertainty that permeates space-time. But that is not quite the case. There is a step between Planck and the apple. To build macroscopic objects, you need a bridge. To make an apple, you first need atoms. We must be clear that when it comes to atoms, language can be used only as in poetry. The experimenters carefully calibrated their laser. Their target, a single hydrogen atom in the center of the chamber chilled to almost absolute zero. Their goal? To take its picture. First proposed in 1981 by Russian theorists, it would take until 2025 for someone to finally make it work. The idea was to hit the electrons and let them scatter away, then carefully measure their velocities in a way that experimenters could reconstruct their original positions. Repeated again and again, each experiment could build up, one shot at a time, a portrait of the atom. And what they saw was bizarre. A series of overlapping rings, clusters and gaps. What they were mapping was not the electrons themselves, but the waves of probability describing where the electrons might be. Each fire of the laser encountered the electron in one particular position. Then another found it on the other side of the atom, for example. Then again and again. Where the waves crested showed where the electron was found most often. The gaps, where it was never found. The atom itself is roughly 100,000 times larger than the electron, and roughly 10 to the power of 25 times larger than the Planck length. And so already, at even these subatomic scales, we are unfathomably far from the deepest structures in the universe. But why is the atom this big, and no bigger or smaller? Indeed, why are all the atoms of the same element identical throughout the cosmos? It's as if every skyscraper in a city was exactly the same, made of the same materials and roughly the same size. There must be something universal and fundamental about them. Of course, the image taken in 2025 of a real atom differs greatly from our popular conceptions of it. A central core surrounded by electrons circling in their orbits. The atomic symbol is everywhere. Indeed, it's become so commonplace that it even stands in as the generic symbol for all of science. It is inaccurate and outdated, but it did represent the first modern attempt to understand what an atom looked like. And the man who created that image and started our journey to a true understanding of why an atom is the size and the way it is, didn't get off to a particularly promising start himself. The young Niels Bohr, who someday would become Heisenberg's mentor and estranged friend, was not an apt pupil in the chemistry lab. He had a fondness for mixing together chemicals that shouldn't strictly be mixed, leading to explosion after explosion. Indeed, he was an expert at breaking glassware, and when students would hear a muffled boom coming from the lab down the hall, the saying was, "Oh, that's a Bohr." And so without a doubt, it was better for everyone that Bohr turned his attention to theoretical physics. At the beginning of the quantum revolution, Bohr had quickly become interested in atomic physics. He was especially drawn in two directions. One was the quantum ideas of Max Planck, that certain quantities in the universe could only act in discrete lumps. The other was the work of his mentor, Ernest Rutherford, who had discovered that whatever the atom was made of, it had a small, dense, positively charged core, a nucleus. Bohr wove these two strands together to paint a first portrait of the atom. At the center of Bohr's atom sits the nucleus, a tight, compact ball of positive electric charge, agreeing with Rutherford's experiments. But what about the electrons, the points of negative electric charge that exist around the nucleus? Other scientists thought that they might form a plum pudding, a thick soup spread out over space. Instead, Bohr replaced this with mostly nothing. Bohr conceived of the electrons as particles, with their relationship to the core governed by electrostatic attraction. Their negative charge pulled as close to the positive nucleus as possible. But this situation should lead to collapse, with each atom unable to hold itself together. So Bohr turned to the quantum world to solve this problem. Electrons could not get any closer to the nucleus because their orbits were quantized. Unlike planets around the Sun, which can have any orbit they please, the electrons had to choose from discrete, specific orbits. For a simple hydrogen atom with only a single proton in its nucleus, the nearest an electron can approach is called the Bohr radius, equal to roughly 10 to the power of 24 Planck lengths. Of course, that is far, far larger than the nucleus itself, which is typically no wider than a few femtometers, about 10 to the power of 20 Planck lengths. That makes even the smallest atoms over 99.99999999999% empty space, with their extent governed by the competing relationships of electrostatic repulsion and the quantization of angular momentum. And so, Bohr's model was a first step into a quantum view of the atom. It would not be the last. Eventually, Erwin Schrödinger would discover why the electrons were confined to these orbits and not others. He was motivated by a bold suggestion made by the French physicist Louis de Broglie. De Broglie had pointed out that light had both wave and particle-like properties, and perhaps the same was true for matter. When you pluck a guitar string, the string vibrates. But the string can't just have any vibration. The ends of the string are locked in place, and so the waves must also terminate at either end. In other words, the waves on a guitar become quantized. Waves can have a single peak at the middle of the string, or 2 peaks, or 4, but they can never have half a peak, or 2/3 of one. Schrödinger envisioned the matter wave of an electron spreading around its orbit, like wrapping a guitar's neck in a circle. The electron's orbit was quantized and confined to certain distances because its wave had to fit. And this is the picture that was finally revealed in the 2025 experiment, not the electrons themselves, but the waves that describe them. And indeed, this is something key when we explore the atomic and subatomic world. These waves are not real in the same sense as a wave on the ocean or the sound waves that ripple through the air. Schrödinger thought they were physical, that matter smeared itself out across space. But he was wrong. Quantum waves are merely waves of probability. They describe where the particle might be located the next time we go looking for it. Where the waves crest, we have a good chance of finding the associated particle, and where they shrink, the chances are low. And so it is therefore clear that the subatomic world is very different to the macroscopic one. The closer you get to Planck scales, either in terms of size or time or energy, the more the wave nature of reality manifests. And the farther away you are, like in the large-scale world, the more the waves are suppressed. Although the more we explore, the more we are finding the line is drawn much larger than we thought. Indeed, the largest object that has been shown to demonstrate a measurable wave nature is a molecule containing around 2,000 atoms. While the world of quantum mechanics would eventually move on from Bohr's initial crude model of the atom, he was right about one important thing. They exist and have the properties they do because of the intersection of different fundamental forces. If we were to imagine flying a tiny spaceship around inside an atom, we wouldn't see much. The vast majority of it would be completely empty space, filled with nothing but vibrating quantum fields. The nucleus would be a tiny point, a dense ball of positive charge sitting far away at the center. The electrons wouldn't be electrons. They would be invisible quantum waves that, should we decide to observe an electron, would snap out of existence and give us a measurement of of its location. And so it is the electromagnetic force competing with quantum mechanics that gives rise to the Bohr radius and the orbits of the electron. And yet deep inside the core of the atom, another series of forces compete with each other to create the nucleus. Atoms are not as simple as their diagrams may suggest. Their nuclei are bundles of even smaller particles, bags of protons and neutrons. Neutrons, as their name might suggest, are electrically neutral. Protons are positively charged, and the two are exceptionally close together, less than a few femtometers apart. At that distance, the electrostatic repulsion is roughly 50 newtons, barely the amount of force needed to lift a watermelon, but that amount of force applied to something as tiny as a proton. Clearly, the atomic nucleus should simply blow itself apart. And yet, it doesn't. Why?
The next station is Torquay. This is a Great Western Railway.
The year is 1934 in Osaka Imperial University, Japan. 26-year-old Hideki Yukawa has been up late, fixated on the mystery of why the atom does not simply explode, just as he has been most nights of the past few years. He has tried dozens of attempts to resolve the problem, but nothing seems to work. Unfortunately, he couldn't turn to experiments for guidance. Like Bohr, he wasn't much of an experimentalist. But one late night, long after everyone else has gone to bed, he is struck with a moment of clarity. The thought suddenly flashed into my mind, he said afterwards, unbidden, like daylight clearing out the morning fog. A new force of nature could be carried by a massive particle, which resisted the electric repulsion and kept the atomic nucleus stable. What Yukawa started that night would change our entire understanding of atoms. But the significance of the moment didn't strike him. Once I'd published my paper, he later said, I felt like a traveller who rests himself at a small tea shop at the top of a mountain slope. At that time, I was not thinking about whether there were any more mountains ahead. We now call this new force of nature Yukawa proposed the strong nuclear force. To pull a proton or neutron out of a nucleus requires working against this force, like resisting gravity to pull an object from the surface of the Earth. And this means that there is an energy associated with each atomic nucleus. All of nuclear power, from the atomic bombs that can level cities to the reactors that light your homes, is based on extracting this energy. Indeed, if we could harness the nuclear binding energy of all the atoms in a sandwich, it would create an explosion comparable to several megatons of TNT, or a powerful nuclear warhead. And yet, in the full modern picture, the binding of the atomic nucleus isn't fundamental. It is an accident. And that's because the protons and neutrons aren't fundamental either. They themselves are small bags of even smaller particles called quarks. And to understand these, it is time for us to enter a place of worship. The central twin spires rise up gracefully, as if it were a modern-day Tower of Babel. It is a spectacular edifice designed to emulate a French Gothic cathedral. Surrounding the main structure are sculptures, a 21-ton arch depicting broken symmetry, a Mobius strip, a hyperbolic obelisk. This is Fermilab, a particle accelerator outside of Chicago, and in 1995 it was here where the last building block of the subatomic universe finally clicked into place. Two teams working with the Tevatron, which at the time was the world's most powerful particle collider, finally found what they had been looking for after 2 decades of effort: the top quark. The top quark had eluded detection for so long because of its gargantuan mass. Indeed, it weighs over 170 million electron volts. That's 180 times more massive even than a proton. This huge mass means that it takes a lot of energy to create it in the first place, and means that it is incredibly unstable, blinking out of existence almost as soon as it's formed. This particle is the king of the quarks, dwarfing the other 5: the bottom quark, the strange and charm quarks, and the up and down quarks. Quarks are ruled primarily by the strong force, which binds them together through the exchange of gluons. In fact, the strong force is so strong that quarks can never be seen individually. If you take 2 quarks and try to separate them, you have to pour so much energy into the effort that new particles pop into existence between them, including other quarks, that immediately bind to the ones you're trying to pull apart. And so the discovery of the top quark locked in place our understanding of the hierarchy of the atom, and why it has the properties that it does. Imagine an apple the size of an atom. Why does its core shrink to a femtometer, and why does the nearest electron sit a nanometer away? Nature likes to build things out of stable foundations, out of entities that can persist for long periods of time. And so atoms exist at the confluence of the strong and electromagnetic forces and the ironclad rules of the quantum realm, where the balance point is reached between all 3. To begin with, there are 6 quarks to choose from, but the most massive ones destroy themselves long before they have the chance to build anything larger. That leaves the lightest ones with the job to create matter, the up and down quarks, which bind together with the strong nuclear force to make the protons and neutrons. The gluons that carry the strong force have mass, giving them a limited range, a little less than a femtometer. But some of the strong force leaks out of the protons and neutrons. This residual strong force easily overwhelms the electrostatic repulsion between protons, but only for a while, up to a few femtometers, before the gluons give out and the electric force takes over. And it is this that determines the size and shape of the nucleus, the crossover point between these 2 forces. Indeed, the largest and heaviest element, oganesson, contains a whopping 118 protons stretching across over 1,000 femtometers. It sits right at the limit of how big a nucleus can be before electrostatic repulsion drives protons away. Of course, like the up and down quarks, there are many cousins to the electrons, but they are all heavy and unstable. Again, only the lightest ones survive long enough to participate in something bigger than themselves, and so the electron feels the attraction of the nucleus, but is prevented from reaching it because it can only squeeze its wave function down to a certain limit. And that is how an atom is formed. Out of the quantum chaos of the Planck scales comes the zoo of particles and forces. Certain particles have certain properties that allow them to build things much larger than a Planck length, and in this way, an atom is built, like a bustling city of quantum activity. But of course, the question still remains: why do the subatomic particles, the quarks and electrons, have these specific masses and sizes? This, we truly do not know. It is one of the great mysteries of modern physics. Like explorers in an unknown jungle, sometimes physicists are here just to observe and record, and save true understanding for future generations. But of course, that is not the end of the story, and far from the end of the structures that come together at larger scales. There are more forces of nature and more places of convergence that make much, much bigger objects possible. Out of the cradle, onto dry land, here it is standing. Atoms with consciousness, matter with curiosity. Stands at the sea, wondering. I, a universe of atoms. An atom in the universe. The Chubut River flows through a desert, cutting a green swath set against the flat-top mesas that make up northern Patagonia. And in 2010, a ranch hand, Aurelio Hernandez, was out for a walk when he stumbled across a strange-looking outcropping. Thinking it was a rock, he brushed away the soil to try to clear it, and kept brushing. Eventually, he unearthed a fossilized bone, almost 8 feet long. Over the next few years, paleontologists uncovered more than 200 fossils at the site, and one of the largest creatures to ever have lived. They are called titanosaurs, and you can see one for yourself at the Field Museum in Chicago. Its name is Maximo, and it stretches 122 feet long from tip to tail and stands 28 feet tall at the head. It lived over 100 million years ago, and when it walked the Earth, the ground quaked under its 70 tons of weight. Maximo is one of the largest creatures there has ever been, but it doesn't even come close to claiming the crown. The largest living fungus is found in Malheur National Forest in the Blue Mountains of eastern Oregon. There, a single fungal colony spans 3.4 square miles in area and is over 2,000 years old. In its time here on the Earth, it has amassed an estimated weight of over 35,000 tons. That is the biggest. But what about the smallest? While biologists debate if viruses count as living creatures, there is no such question surrounding bacteria. The smallest known free-living bacteria is Pelagibacter ubique, translated as ubiquitous oceanic bacteria, with a length of only a few hundred nanometers. But despite its minuscule size, the species is so numerous that the total mass of all these bacteria outweighs all the fish in the world's oceans combined. And so life stretches across quite a large size range. Indeed, the leap in size between a bacterium and the Malheur National Forest fungal colony is much greater than that of an atom to a bacterium. And yet, when we arrive at this scale, the scale of life, some truly bizarre physics starts to occur. We know that at the smallest scales, between the Planck scale and the simplest living creatures, the universe obeys relatively simple and straightforward physical laws. Forces of nature do their work over certain distances, and particles respond in turn. But there is no equation in physics that can predict how a bacterium might consume food, or how a blue whale might sing its song. Standing between the laws of nature and biological systems aren't just many orders of magnitude. There is also an unimaginable jump in complexity. And this is the concept of emergence, how simple rules can lead to surprisingly complex behaviors. And the best way to illustrate this is through a game. To begin with, imagine a series of cells forming a grid. Choose whichever cells you want to be alive. They are activated. Then proceed as follows. Any live cell with fewer than 2 live neighbors dies, as if by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. But any live cell with more than 3 live neighbors also dies, as if by overpopulation. And finally, any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. This is the game of life, created by mathematician John Conway. First appearing in an issue of Scientific American in 1970, it shows how complexity can arise from a set of simple rules. Indeed, 2 games of life with only slightly differing starting arrangements can lead to wildly different outcomes, with different patterns, arrangements and structures appearing and disappearing,